Today we will take the topic that is energy levels. Energy levels of transition metal ions. Turn wave functions. And spin orbit coupling. First, in the introduction, we will cover few points such as quantum numbers, term, and microstate. First, we will see quantum numbers. There are four types of quantum numbers, and these are principal quantum number, second is orbital quantum number, third is magnetic quantum number, and fourth is spin quantum number. Let us see these numbers one by one. First, principal quantum number. It is denoted by the letter small n, and this number gives the main energy level in which electron is present. This number also gives the effective distance of nucleus, effective distance of electron from the nucleus. It can have positive integer values, that is n is equal to 1, 2, 3, 4, etc. The second quantum number is orbital quantum number or azimuthal quantum number, and it is denoted by letter small l. This number gives the sub-energy level of electron. It also gives the shape of the orbital in which electron is present, and its values depend upon the value of principal quantum number n, and it can values from 0 to n minus 1. The third quantum number, that is magnetic quantum number, it gives the orientation of orbital containing electron in the space, and it can have values or values of magnetic quantum number depends upon the values of L, and these are denoted by the letter ML, and it can have values from plus L to minus L. For example, when L is equal to 1, magnetic quantum number values may be +1, 0 and -1. And the last quantum number, that is spin quantum number, it is denoted by ms, and this number gives the spin of electron about its own axis. This value of spin quantum number is either +1/2 or -1/2. When the electron spins in a clockwise manner, then the spin quantum number is +1/2, and when it spins anti-clockwise manner, the spin quantum number is -1/2. So this is about the 4 quantum numbers. So we can summarize these quantum numbers on which the construction of periodic table is based. When the principal quantum number is 1, the orbital quantum number L, which can have values from 0 to n-1, may be 0 and 1. The magnetic quantum number ml values for orbital quantum number 0 are ml values are equal to twice L plus 1 or plus L to minus L. Therefore, the ml values are 0 to -0, that is only 1, and ms values are +1/2 and -1/2. So, when n is 1, the energy level is first energy level, and it can accommodate only 2 electrons, one with spin quantum number +1/2 and other with spin quantum number -1/2. Therefore, there is only one orbital, and it is one s orbital in the first energy level. When n is 2, that is principal or main energy level is 2, then L can be 0 and 1. So, when L is 0, ml values are 0 to 0, that is -0, and when L is equal to 1, in the second principal quantum number, then ml values are +1, 0 and -1. So for this 0 ml values, the 2 electrons can be accommodated in this orbital having opposite spins. So the orbital corresponding to n is equal to 2 and L is equal to 0, ml is equal to 0, the orbital is 2s orbital, and for ml +1, -1, +1, 0 and -1, for each ml value there are 2 electrons with +1/2 and -1/2, +1/2 and -1/2. So these 3 suborbitals constitute the 2p orbital, which can contain total of 6 electrons. When the n is equal to 3, then L values possible are n 0 to n-1. So 0 to n-1, So L values are 0, 1 and 2. When L is 0, ml is 0. When L is 1, ml can be plus 1, 0 and minus 1. And when ml orbital quantum number L is 2, ml values are plus 2, plus 1, 0, minus 1 and minus 2. So when for third shell, when ml is 0, again here 2 electrons and the orbital corresponding is 3s orbital. For plus 1, 0, minus 1, again total 6 electrons, and so the orbital is 3p orbital. And for these 5 ml values, the total 10 electrons, 2 in each orbital, and therefore these are the 3d orbitals. In this way, the first shell contains only one orbital, so there could be only 2 electrons, one with ms value plus 1/2 and other with ms value minus 1/2. So in the first period there are only 2 elements, that is hydrogen and helium, in which electrons enter the 1s orbital. In the second period there are 2 types of orbitals, 2s and 2p orbital. 2s orbital contains 2 electrons and 2p orbital contains 6 electrons. Therefore, in a second energy level, there are, or in second period, there are total 8 elements in which electrons enter one by one in 2s orbital and 2p orbital. In the third period, there are total 3s, 3p and 3d orbital, 5 suborbitals of 3d, 3 suborbitals of 3p and 1 orbital of 3s. So the third period, in the third period there are total 10 plus 6 plus 2, that is 18 elements are present in the third period, in which the third principal shell is filled. In this way, the base of the periodic table is the quantum numbers. Next, we will see what is term. So, what is term? Again, the term is the energy level. It is the energy level which arises from the given D configuration, for transition metal ions. The term is designated by the symbol as X twice S plus 1 and G. Here the significance of these terms, here X is term symbol. X is term symbol and it depends upon the values of L and S. What is L? L is the total orbital quantum number. L is total orbital quantum number for the given D configuration, and S is the total spin quantum number, of all the electrons. Here this J value, it is the spin orbit coupling, or it is also called as total angular momentum quantum number. Here this term 2s plus 1, it is called as spin multiplicity of the term. It is called as spin multiplicity of the term. Means the total spin values possible. Total number of spin values possible for the given electron configuration. The spin multiplicity of the term depends upon total spin for the given configuration. Suppose if the S, that is total spin of the configuration, is 0, means all the electrons are paired, then twice S plus 1 will be equal to 2 into 0 plus 1, that is it will be equal to 1, means spin multiplicity will be 1 and the term will be called as singlet. Only one spin value is possible for the configuration, means all the electrons are paired. When the total spin is 1/2, that is one electron is unpaired, then spin multiplicity will be 2 into 1/2 plus 1 is equal to 2 will get cancelled and spin multiplicity will be 2. Then the term is called as doublet. When the total spin is 1, then 2 into 1 plus 1, it will be 3. Spin multiplicity will be 3, means the term is triplet. When it is 3 and half, then 2 into 3 by 2 plus 1 is equal to 2 will get cancelled. It will be 4 and the term is called as quartet. If the total spin is 2, then the spin multiplicity comes to be 5 and the term is called as quintet. And lastly, when it is total spin is 5 by 2, then 2 into 5 by 2 plus 1, 2 to cancel, will get 6 and the term is called as sextet. In this way, the spin multiplicity of the term twice s plus 1, it depends upon the total spin of the configuration, that is number of unpaired electrons. Next, we will see what is microstate. Microstate. Microstate is simply the representation of electron. Microstate, or it is called as term wave function, it is representation of electron with the help of ml and ms value. Representation of electron or electrons with the help of total orbital quantum number value and total spin quantum number value. The total number of microstates, that is term wave functions, are possible representations or possible combinations of total orbital quantum number and total spin quantum number can be obtained by the n factorial equation. So, total number of microstates is equal to n factorial by small n factorial into n minus n factorial. What is n? Capital N is the electron capacity. Electron capacity of the orbital in which electron is present. Small n is the actual number of electrons present in the orbital. For example, we will obtain the number of microstates for different electronic configuration. First, consider NS1 configuration, the s orbital containing single electron. So for this configuration, the total number of microstates is equal to, we will put this equation, n factorial and small n factorial into n minus n factorial. For s orbital, there is single suborbital, so it can contain only 2 electrons, one with upspin and other with downspin. Therefore, for s orbital, capital N, that is electron capacity of the s orbital, is 2. Small n, that is actual number of electrons, is 1. Therefore, n minus n will be 1. So by putting these values of n, small n and n minus 1 in this equation, the total number of microstates can be calculated as 2 factorial, n is equal to 2, so 2 factorial by small n 1, 1 factorial into n minus n 1, that is 1 factorial. It can be solved as 2 into 1 by 1 into 1. So the answer comes as 2 by 1, that is 2. Means for single electron in s orbital, 2 arrangements are possible, that is, one is with upspin and other is with downspin. So total number of microstates for NS1, it is 1. And these microstates, these 2 microstates can be shown as, for s orbital, n is equal to 0. Now that we'll see afterwards. So for NS1 configuration, total number of microstates comes to be 2. The single electron can be arranged in the single orbital for first time with upspin and for second time with downspin. Suppose the NP1 configuration. NP1 configuration. Totally there are three suborbitals for the in the p orbital, one with +1 ml values, +1, 0 and -1. So for p orbital, the capital N, that is electron capacity, is 6, that is 6 electrons can be accommodated in a total of these 3 orbitals. So total electron capacity of p orbital is 6. Here small n, actual number of electrons given, is 1. Therefore n minus n, capital N is 6, small n is 1, that is 6 minus 1 is equal to 5. So total number of microstates for the NP1 configuration again can be obtained by n factorial equation. N minus small n factorial is equal to, n is 6, so 6 factorial by single electron 1 factorial into n minus n, that is 5 factorial. And further it can be solved as, here in the denominator there is 5 factorial, so 6 into 5 factorial by 5 factorial into 1. 5 will get cancelled, and so total number of microstates for NP1 configuration comes to be 6. What is meant by the 6? It means the single electron can be arranged in these 3 suborbitals in 6 different ways, which have different combinations of ml and ms values. So which are these 6 possibilities? the first possibility is this one, second possibility is this one, third possibility is this one, and fourth, fifth and sixth possibility, fourth one, then fifth one and then sixth one. So all these 6 arrangements have either ml value different or ms value different. Then one more example that we'll see is the ND1 configuration, or the ND1 configuration for transition metal ions. For d orbital, there are 5 ml values, 1, 2, 3, 4 and 5, from +2, +1, 0, -1 and -2. So we have to arrange this single electron in a different ways in these 5 d orbitals. So total capacity, there are 5 suborbitals, each orbital can accommodate a pair of electrons. So capital N, that is total electron capacity of the d orbital, is 10. The actual number of electrons present in the given configuration is 1. Therefore, n minus n will be 10 minus 1, that is 9. So, total number of microstates for ND1 configuration, again n factorial by small n factorial, n minus n factorial, capital N is 10 factorial by small n is 1 factorial into n minus n, that is 9 factorial. So again in the denominator there is 9 factorial, therefore 10 into 9 factorial by 9 factorial into 1 into 1. 9 will get cancelled. So answer 10 by 1 is equal to 10. It means this single electron can be arranged in these 5 suborbitals in a 10 different ways, and each representation will have different combination of ml and ms value. So again, which are these 10 possibilities? First is this one, single electron may be placed in this with upspin, or in this, or in this, or in this, or in this. In this 5 combination, ml values are different and ms value is same, and in other 5 combinations the ml values are different but ms value is same. It may be arranged in this fashion, or in this fashion, or in this fashion. So the total 10 arrangements are possible for the single electron in d orbital. One more, NF1. You know that there are 7 suborbitals, 1, 2, 3, 4, 5, 6 and 7 with +3 to -3 ml values. So this single electron, actually we can see that single electron can be placed, these 7 ml values for first time with upspin, and in all these ml values for second time with downspin. So total representations comes to be 14, and that we'll see with the help of n factorial equation. So for F, as there are 7 orbitals, the total capacity is to contain 14 electrons, that is capital N is 14, small n given it is 1, and n minus n, that will be 14 minus 1, that is 30. So for NF1, total number of microstates will be n factorial and n minus n factorial. Capital N is 14, so 14 factorial by small n 1 factorial into n minus n 13 factorial. So again in the denominator there is 13 factorial, so the 14 factorial can be splitted as 14 factorial so 14 into 13 factorial. So 1 into 13 factorial cancelled. So 14 microstates are possible for single electron in f orbital. So this is for single electron. So for NS1 configuration, the total number of microstates possible, microstate, that is representation of electron with the help of ml and ms value, is 2. For NP1 it is 6. We can arrange single electron in a 6 different ways. ND1 it is 10, and for NF1 it is 14. So this is very simple case which we can solve even without n factorial equation. Now see, NS2, for NS2, you know, for s orbital n is equal to small n is equal to 2, therefore n minus n will be 0. So total number of microstates for NS2 configuration, n factorial, that is 2 factorial by small n factorial, 2 factorial into n minus n, that is 0 factorial. So the solution comes to be 2, that is value is 0. It means single representation is possible, and that representation for NS2 will be one electron with upspin and second electron with downspin. There is no other possibility. So only one possibility is there. For NP2 configuration, now it is easy to see the values of n and small n, capital N, n factorial, capital N is equal to, for P it is 6, small n is equal to 2, therefore n minus n will be equal to 6 minus 2, that is 4. So by solving the equation, 6 factorial by 2 factorial into 4 factorial is equal to, so here the largest factorial is 4 factorial, therefore we can split 6 factorial up to 4 factorial, 6 into 5 into 4 factorial by this 4 factorial into 2 into 1. So 4 will get cancelled, 5 into 6, 30, 2 into 1, 2. So total 15 microstates are possible for NP2. So for NP1, the number of microstates were 6. But with increasing electrons in p orbital, the recombination possibility increases and number of microstates increases to 15. Similarly, for ND2 configuration, here you know n is equal to 10. Here now small n is equal to 2. Therefore, n minus n will be equal to 8. By using n factorial equation, capital N 10 factorial by small n 2 factorial into n minus n, that is 8 factorial. Denominator contains 8 factorials, therefore 10 into 9 into 8 factorial by 8 factorial into 2 into 1. So 8 will get cancelled. Here 2, 5. So total 9 into 5, 45 microstates are possible. Here again you can see difference. For ND1 configuration, total microstates possible were 10, which increases to 45 for ND2 configuration. So we can observe that with increasing number of electrons in the degenerate set of orbitals, number of microstates goes on increasing. The same thing is with NF2. For F orbital, n is equal to 14, small n is equal to 2, therefore n minus n is equal to 12. By putting these values in equation, 14 factorial by 2 factorial into 12 factorial, we can solve 14 into 13 into 12 factorial by 12 factorial into 2 into 1. So 12 gets cancelled, 2, 7. So answer 91. So again you can see that for an F1 configuration, the total number of microstates were 14. 7 orbitals, and in each orbital 2 possibilities for single electron, therefore total 14, which increases to 91 for an F2 configuration. So in this way we can use the n factorial equation to calculate total number of microstates for the given configuration. So this is for plain orbital configuration. We'll see one more configuration, that is T2G2. T2G2 configuration. So this configuration, it is not for the free transition metal ion, but it is for the transition metal ion in the octahedral complex. So T2G, it is a triply degenerate. You know that the set of 5d orbitals, which is degenerate in the free metal ion, when the metal ion forms complex, it gets splitted into a higher energy set of 2 orbitals and a lower energy set of 3 suborbitals. Lower energy set is called as T2G and it is Eg. So 2 electrons in T2G, so configuration is T2G. So the orbital degeneracy, like p orbital, the orbital degeneracy of T2G set, it is 3, therefore T2G set can accommodate total of 6 electrons. So for T2G orbital, capital N is equal to 6. The number of electrons actually present, that is N, is equal to 2. So N minus N will be 4. By putting this in equation, total number of microstates for T2G2 configuration will be 6 factorial by 2 factorial into 4 factorial. So 6 into 5 into 4 factorial by 4 factorial into 2 into 1. 4 factorial will get cancelled, and 2, 6, 3. So there will be 15 microstates. So we have already seen that for P2 configuration and P2 configuration, the total microstates were 15. Similarly, for T2G2 configuration also, the same number of microstates is observed. So we can say as NP2 and T2G2 configuration will have the same number of microstates. One more configuration, which is EG configuration. So let us see number of microstates for EG2 configuration. Again, just we have seen that EG set consists of 2 suborbitals. So each one can accommodate 2. So 2 to 4. So for EG set of orbitals, capital N is equal to 4. Actual number of electrons N is 2, and the N minus N will be 4 minus 2, that is 2. So N factorial by small n factorial into N minus N factorial will be 4 factorial by 2 factorial into 2 factorial is equal to 4 into 3 into 2 factorial and 2 factorial into 2 into 2. 2 factorial gets cancelled, 2, 4 by 2, 2. Therefore, total 6 microstates are possible for EG configuration. So, this is about the representation of electrons with the help of ml and ms values, which is called as microstate. So we can revise these 3 points, that is first quantum numbers, then term, and third microstate. So quantum numbers are the numbers which are used to designate the electron in an atom with respect to its energy and location, and there are 4 quantum numbers. These are principal quantum number, orbital or azimuthal quantum number, magnetic quantum number, and spin quantum number. Term, it is the energy level which arises for the given configuration, and it is designated by the symbol twice x twice s plus 1 and j value. And microstate, it is the representation of electron with the help of ms and ml value, and number of microstates for given configuration can be obtained by the n factorial equation. And few examples just we have solved about obtaining the total number of microstates. In case of this term, the term symbol x, it depends upon the value of L. It depends upon the value of L. What is L? L is the total orbital quantum number. L is total orbital quantum number. And let us see what are the term symbols for different L values. When the L is equal to 0, then term symbol x will be, when L is equal to 0, x will be, the term symbol will be s. When the L value is 1, the term symbol will be capital P. When the L value is 2, then the term symbol is capital D. When the L value is 3, the term symbol is capital F. Like orbitals have small letters. When the L value is 4, the term symbol is G. When the L value is 5, term symbol is H. And when the L value, total orbital quantum number, is 6, then the term symbol is R. So in this way, we have learned about different quantum numbers, what is mean by term, what is mean by spin multiplicity, how it is obtained, and what is mean by microstate, and how microstates can be calculated for given electronic configuration. And that's all.